Problem number 8. W is the solid region right here. S is the boundary surface. F is this vector field. We need to verify the divergence theorem that the double integral over S of f dot n d sigma is equal to triple integral over W of the divergence of f dv. What's going on here? What's going on here? So this region, it looks like this. So Z is at least 3, but at most 4, because this x squared plus y squared is going to be negative. It's some kind of little parabolic cap here floating around in space. So like here, Z is equal to 3, here Z is equal to 4. And the projection, if we project this down to the xy plane, then this is going to be, what is this curve right here? Maybe is a better way to ask and answer this question. This is when these two intersect. 3 is equal to 4 minus x squared minus y squared. Subtracting 3 and rearranging, x squared plus y squared is equal to 1. Okay, so that shows what's going on here. So let's go ahead and verify the divergence theorem. So to verify the divergence theorem, this is a two-part process. We need to compute both of these integrals here and make sure we get the same answer. So I'm going to start with this side right here, the divergence side, the triple integral. Okay, what's going on here? We need the divergence here. Partial derivative of this with respect to x is 1. Partial derivative of this with respect to y is 1. Partial derivative of this with respect to z is negative 3. So the divergence is just negative 1 here. So we're integrating negative 1, a nice constant over this region. We want to express this region in cylindrical coordinates, triple integral. So we'll need bounds on theta, r, and z. So theta runs from 0 to 2 pi, one loop around the circle. R is x squared, r squared is x squared plus y squared. We could see from this, r can be anything from 0 to 1. And then z, the bounds for z are given to us in the problem once we replace x squared plus y squared with r squared. So this integral is equal to, 0 to 2 pi, 0 to 1, 3 to 4 minus r squared of negative 1 r dz dr d theta. The theta terms will give us a factor of 2 pi. Let's see. Now we need to integrate with respect to z here. We'll just get negative r times z. Plug in 3 to 4 minus r squared. And so this will give us negative r times 4 minus r squared minus 3. And this will be 1 minus r squared. Okay, so what do we have here? Distributing this out gives us negative r plus r cubed dr. And what do we end up with? Negative r squared over 2 plus r to the 4th over 4. Plug in from 0 to 1. And 2 pi times negative 1/2 plus 1/4 is negative 1/4. So this is negative pi over 2. Okay, one side down. This is negative pi over 2. Okay, so now we need to verify this, that we get the same answer on this side here. So for this integral, the double integral over s, the f dot n d sigma here, there's two separate chunks that we have to do. So the surface of this parabolic shaped cap here has two different chunks. One is the parabolic side of thing. The other is the base of it pointing down. We need to make sure our region is completely surrounded in order to apply the divergence theorem. So common mistake would be to forget the floor here. Okay, so let's go ahead and do this. So I'm going to just write this as S in this form, S1 plus S2, so we'll say S2 is the floor and S1 is the cap part of the things. So for S1, how do we parameterize this? This is z is equal to 4 minus x squared plus y squared. So we could parameterize S1 by r of xy is equal to x, y, and 4 minus x squared plus y squared. With the corresponding normal vector, the rx plus ry, we can just copy off of this chart here. It's going to be 2x, 2y, and 1. Okay, what else do we have to do here? We need f of r of xy. What was f? It's been a while since we've seen it. F is here. So y plus x is just y plus x. Y minus x is still y minus x. And that 1 minus 3 times z right here is 4 minus x squared plus y squared. And then we need f dot product with this right here. And so it's going to be 2x times this is 2x squared plus 2xy. Plus 2y times this will give us 2y squared minus 2xy. And 1 times this will give us 1 minus 12. And then minus times minus is plus 3x squared plus 3y squared. Okay, so canceling and simplifying, those cancel. That gives us negative 11. And then 2x squared, 3x squared, that's plus 5x squared. 2y squared plus 3y squared is 5y squared. Okay, what is up next? Well, we actually need to integrate this over the region. What are the bounds here on x and y? Well, x and y, the constraint here is coming from x squared plus y squared can be at most 1. So we're going to switch this to, unsurprisingly, polar coordinates. The double integral over S1 of f dot n d sigma is equal to theta runs from 0 to 2 pi, r runs from 0 to 1 of negative 11 plus, this will give us 5r squared. And then r dr d theta. The theta stuff gives us a factor of 2 pi. This becomes negative 11r plus 5r cubed. And so integrating that gives us negative 11 over 2 r squared plus 5r to the 4th over 4. Plug in from 0 to 1. And so we end up with negative 11 over 2 plus 5/4 times 2 pi. Let's simplify this real quick here. 2 pi times, this will be negative 22 over 4 plus 5/4. So 2 pi times negative 17 over 4. So negative 17 over 2 pi. Okay, so we did this calculation. Now we need to do the base. And we need to make sure the base is oriented so it's pointing downwards. Because in the divergence theorem, these always have to be pointing away from the region in question. So how do we parameterize this, this right here? Well, double integral for S2 of f dot n d sigma. So our parameterization. So realize what's going on here. X and y are just x and y, and z is going to be 3 here. So x, y, and 3 will work for our parameterization. Again, x squared plus y squared can be at most 1. The normal vector, okay, reading it off of our chart here, the x and y partial derivative of the 3 are both 0. So it looks like we should just go 0, 0, and 1. But this is assuming that we have an upward pointing normal vector. We want a downwards pointing normal vector. So how do we fix this? We throw in a negative sign there. Okay, so this is our r of x, y. There's our cross product here. F of r of x, y is equal to y plus x, y minus x. 1 minus 3 times z. Z is 3 here. And then f dot product with rx cross ry here. So this dot product, this is 0 plus 0 minus 1 minus 9. And this ends up as 8. So we are going to integrate here. Theta, let's see here. So again, we need to change the polar coordinates. Theta runs from 0 to 2 pi. R runs from 0 to 1 of 8r dr d theta. And a little bit of thought should convince you that this ends up as 8 pi. And so here is the punchline. So the triple integral of the divergence over W, we got that as negative pi over 2. And then, oops, only double integral here. The integral over S1 of f dot n d sigma plus the integral over S2 of f dot n d sigma is going to be negative 17 over 2 pi plus 8 pi. And yes, this is equal to negative pi over 2. I was a little bit nervous there. I'm working this blindly. I didn't work out ahead of time. I was hoping everything would work out. 15 minutes later, everything checks out. Thumbs up.